Hello everyone, this is a video solution for the question 2 in tutorial 4, which is about the ideal gas equations. So this question is actually quite similar to the first question Q1, which we just solved. So basically we just needed two equations to calculate the volume of the tank in liters. So first of all, the first equation is that we use what we call PV equals MRT. So this is what we call ideal gas equation. Okay, and then we need another equation, which is R is equal to R0 divided by M to find out what we call this specific gas constant. Okay, so depending on what gas it is, in this case, so it's oxygen. So we know the molar mass of oxygen will be 32 kilogram per kilomole, and this will be given to you. Okay, so what we're going to do is actually we need to calculate R specific gas constant for oxygen. So it's divided R0 divided by M. Okay, so R0 is always a constant which will be given to you, divided by M. So for oxygen, M is 32. So, and then we can calculate okay, be very careful about here. The unit on the top is kilojoule, and then we need to convert that to joule in the following calculations. Okay, so according to this equation, PV is equal to MRT. Now we're going to calculate the volume of the tank in liters. Okay, so we're going to calculate the volume here. If I'm going to divide P on both sides, so we can get the volume, okay, which is equal to MRT divided by P. Okay, so now what we can do is that we can input all the figures of these variables and convert them to SI-based unit at the same time. So M, so we can have a look. M is 1.5 kilogram. It's already SI-based unit, so we're not worrying about that. Times R. Okay, R is here. As I said, we need to convert that kilojoule to joule by times 1000. T, so T should be Kelvin temperature. So we check in the question. We know that temperature is 168 Kelvin, so it's already in Kelvin now, so you don't have to, you can't actually add that to 273 because it's already in Kelvin. P, so P is the pressure. Have a look, the pressure is 42 bar, so again we need to convert that 42 bar to Pascal. And then, based on this, we can calculate the volume, because we already used SI-based unit for each of them. So the final answer must be SI-based unit as well. So this must be, okay, cubic meter. And because in the question you're asked to give the volume of the tank in liters, so you have to convert that to liters by multiply by 1000, which finally will give you 15.6 liter. Okay, so that's for the first one. So for the second question, so the gas is cooled down and the pressure drops to 36 bar. So it's a cooling process. So this process, and we need to determine the temperature of the oxygen after cooling in Kelvin temperature. Okay, so the method we're going to use here, actually, I would recommend you that you make use of, in the formula sheet. So we have another formula here. Okay, PV divided by T is equal to constant. If you have a look at the equation here, if I divided T over here, so PV divided by T is actually equal to MR. Okay, so for a fixed for a closed system, the mass is fixed, R is fixed, so that this is constant. Okay, so which means that during a process, the P times V divided by T is a constant. So we're going to make use of this equation for the second question here. So during this process, this cooling process, we have P1 V1 over T1, okay, is equal to P2 V2 over T2. And also, if you have a look at the question here, so it says rigid tank. Okay, as I mentioned earlier in the lecture, for any rigid tank, so any process happening in a rigid tank have the same volume. So the volume won't change during any process here. So once you see rigid tank, basically means that this process must be a constant volume. Constant volume process as well, which means that V1 and V2 are the same. So you just cross these two out. Okay, so what do we need to calculate is the temperature of the oxygen after cooling. Okay, so this is the end state of a process, which is actually T2 here. Okay, so according to this, I'm going to rearrange to get T2. Okay, so T2 had to cross multiplication, so T2 is equal to P2 times T1 divided by P1. So we just need to rearrange it. P2 times T1 over P1. As you can see here, we have P2 over P1. So actually you don't need to do any conversion of units here because you're going to divide them anyway. So P2 here, let's have a look. P2 is the final pressure, which is 36 bar. P1, initial pressure, which is 42 bar. Temperature, T1 means the initial temperature, which is 168 in Kelvin. Okay, so this is quite a simple calculation now, and then finally we get 144 Kelvin. Okay, and this is exactly the T2 temperature of the oxygen after cooling. Okay, so that's a solution for question 2 in tutorial 4.